Okay, so we have one more topic to cover before we round out this bit about energy and conservation. Okay, so today we're going to talk about conservation of energy and potential energy diagrams. And after that, we'll be moving on to fun things like collisions and momentum and stuff like that. Because so far we've mostly been dealing with single objects. Okay. So today I sort of want to bring together some ideas, show you one or two new ideas, and do a bunch of examples. And the next time we'll move on to a new topic. Okay, so we've been thinking about how things move, right? For example, if you have a projectile, right? You have an object here, and you throw it up in the air, and it comes back down, right? It starts here with a lot of kinetic energy. So, a lot of kinetic energy, and no potential energy, right? Here where you're throwing it. Here at the top, all that kinetic energy has been turned into potential energy, right? And then back here, you got kinetic energy again, and almost no potential energy. All right, so the energy just shifts from kinetic to potential and back. You guys know that well. Why is it that you end up with the same amount of kinetic energy here as you started? Gravity's conservative, right? All the potential energy that's created gets turned back into kinetic energy. Also, in this simple model here, there's no air resistance, there's no friction, right? This is an isolated system from the rest of the universe, and so that's why there's conservation of energy for this guy, right? If we added air resistance, then you'd lose some of the kinetic energy, you wouldn't go as high, right? And on the way back down, some of the potential energy would get turned into heat of the air around it, or wind, or heat of the object, and you wouldn't get all this kinetic energy. Because then, in order to have conservation of energy, we'd have to include all of the air also in our system, right? If we only consider the ball, then there's conservation of energy with no air resistance. Okay. And the interesting thing is that the ratio here, kinetic energy to potential energy, depends only on the height, right? Doesn't matter how far out x you are, it only depends, the ratio only depends on the height, okay? And we've seen other systems where things matter only in the y direction, right? Like we talked about if you have a block and it gets moved by some force to some other location, right? And you have, on this block you have some force, and you have gravity, right? Now if gravity is only in y, right, then to calculate the work done by gravity, you only need to know this, delta y, right? So the work done by gravity is only affected by the difference in height. Why? Well, you might say because gravity is a conservative force, or you might think about the motion of the object dotted with the direction of gravity, right? Gravity only points down, and so the work only matters in the down direction. Okay, what about a slightly more subtle example? What if you had something like this? All right, you have a skateboarder on a track. Okay, imagine that's a perfect semicircle. Right. And he starts here. Right, and ends up over here, of course. Oops. Okay. So when he starts up here at the top, gravity is pulling him down, right? And if this is in fact totally vertical, what is the normal force on the skateboarder at this point? 0, right? Because he's not exerting any force on the circle. He's basically falling next to it. Right? As soon as he, and then he falls onto this first part of the curve, and then it starts to push back. So what about over here? Here, right? He's got gravity, of course, pulling him down. And he's got a normal force, which is pushing out this way, right? Right through his head. It's a normal force. Now, gravity between here and here, there's some delta y, of course, so of course there's some work done by gravity. What about the normal force? Does the normal force do any work?
No.
No, why not? Right, the normal force is always perpendicular to the surface, and he's moving along the surface, so the normal force is doing no work in this case, right? So here, if there's no friction, right, again, there's no friction, there's conservation of energy, right? His potential energy turned into kinetic energy. It doesn't matter that he took a semicircular path or if there was a wiggle in here, right? The normal force is always perpendicular to the surface that he's on, so as long as his skateboard is small enough to stay on the surface, the normal force is going to do no work. Okay? Now, let's imagine another case, more realistic, when there is some friction here. So what's going to be the direction of the force due to friction? Opposite of his motion, right? So along the surface, but the opposite direction that he's going, right? So is friction going to do some work? Yeah, negative work, right? It's always pointing in the opposite direction of his motion, so it's going to steal some of his potential energy into heat rather than into kinetic energy. So friction here does some work, right? Okay, so similarly, if you have, here's another example they talk about in the book. You have a rock in a hemisphere, right? It starts here. And it says it's a frictionless bowl. Okay, so no friction. Right? It starts here. How far is it going to go if it comes down and goes back up? How far up is it going to go? Exactly the same height. And the reason is conservation of energy, right? The potentials turn into kinetic and turn back into potential energy. Because there's no friction here, all the potential energy goes to kinetic energy and then back to potential energy. If there was friction, of course, it would slide down, not come quite as far up, because some of the energy would be lost due to heat, right? And then back, and then it would slowly oscillate in this damped oscillation. And you know what that means if you take the differential equations, and eventually come to rest in the middle with all of the potential energy turned into heat, right? Okay, that's pretty simple stuff. So in this case, we have conservative forces like gravity, right, where you can take the energy and retrieve it, and non-conservative forces like friction, right? So non-conservative like friction. Okay? What if we took a different example and we said, we took a spring and a block, right? Is the force from a spring conservative or non-conservative? Somebody's shaking their head. Does that mean non-conservative? Tell me why.
I think it's conservative because, if an object hits the spring, it'll compress, and once it gets back to the point of decompression where it originally hit, the amount of kinetic energy at that point will be the same.
Right, so it's a conservative force if it's reversible, right? If you can get back the energy that you've turned into potential energy. So if you take your kinetic energy, put into this kind of potential energy, and you can get it back, then it's a conservative force. In the case of friction, you can't unless you have some way to capture the heat of friction and turn it back into kinetic energy, right? But in the case of a spring, if you stretch this guy out, right, so he's over here, then it has potential energy. The potential energy is turned into kinetic energy, but then it's turned back into potential energy, right? So there's no loss of energy here, right? So the spring force is also a conservative force. If you have a system with just a spring force and kinetic energy, there's no loss of energy, right? The spring force, similarly, depends on only the position, right? Okay, so now there's a useful way to think about these things. to think about the connection between forces and energy. Okay, so let's draw the function of the forces. All right, so let's do gravity first. Okay, so in the case of gravity, so this is the force, and this is the potential. Okay, so in the case of gravity, I guess this should be y. What is the force of gravity as a function of y? Function of height. Yeah, it's basically constant, right? Assuming you're close to the surface of the Earth, it's just constant. Okay? Now, and what about the potential energy? What does that look like as a function of height? Linear and positive, right? Because this is mgy, right? So it goes like this, right? Now, does it matter where I put the 0? Potential energy? I mean, I drew an axis here. Does it matter where I put the 0? No, why doesn't it matter?
It's only the change that matters.
Sorry?
It's only the change that...
The change that matters. What do you mean that matters?
Well, it's going to have some potential energy. Like, you could say that this has potential energy, but if it's not moving anywhere, it's not relevant. So if it doesn't change...
It doesn't have any physical impact, right?
Yeah.
Sometimes we have mathematical models that have mathematical consequences but no physical consequences, right? For example, you could have negative solutions to some quadratic equation. It's not a physical solution. You could have mathematical answers that are not physical answers. So in this case, potential is not a physically measurable quantity, right? You can't measure potential. What you can do, however, is measure force, because force is mass times acceleration. The relationship between these two guys is force is the negative derivative of the potential. And this makes explicitly mathematically clear why the value of this doesn't matter. Because force is the physical quantity. If you add a constant to u, it doesn't change the force, right? Because it doesn't have any, the constant doesn't have any derivative with respect to x. So now take this potential, which is linear, uy, take its derivative, and you get a constant, which is exactly the force you see. So a linear potential energy function like this generates a constant force. Now, there's an easy way to think about this using your intuition, where you say, well, if I imagine this potential shape to be the shape of a hill, right? Imagine that rather than just being a function, say, this is a physical object and it's a hill, and I put a ball on it, which way would it roll? Well, in this case, obviously, it would roll down, right? So the force is to negative y. So here, I should have put a 0 somewhere, right? The force is definitely negative, right? Gravitational force is negative in water. So you can either just use your intuition and say, what would happen if I put a ball on this potential on this hill, or you can do it mathematically. You can say, if I have a potential with this dependence on y, I can derive the force on an object in that potential by just taking the negative derivative. Okay, let's do a slightly more complicated case of a spring, and then we'll do some exercises to get the hang of this, because it might be a new concept. All right, so here we have force as a function of x, potential as a function of x, right? So what does the force look like in the case of a spring? It's a negative kx, right? So if this is 0, the force itself is linear. So what does that mean about the potential? It's parabolic, right? I mean, if you know this relationship and you have the force, then you can get the potential by integrating, right? But we already know the potential energy of a spring is 1/2 kx squared just by doing the integral of the force started with the distance, right? So these in red. So this is the potential of a spring. Now similarly, with thinking about it as earlier, what would happen if you put a ball here? Well, we just did this example, right? You would roll down to the middle, picking up speed, and then come back up to the same place, and then come back down. And in fact, what happens if you take a spring and you pull the spring back some distance? Well, it oscillates around the equilibrium point, right? Because it receives a positive, sorry, you guys totally let me draw this the wrong way. It receives a negative force when it has a positive value, pushing it back this way, just like a ball rolling up this hill would receive. Right? And it receives a positive force pushing it this way when it rolls up this hill. Okay, so the only point I wanted to make is the relationship between force and potential energy for conservative forces.
So shouldn't the parabola be negative then too? Oh.
This guy is, but that's a good idea. Let's think about that. So the nice thing about this is it gives you a rule to derive the force just from the potential. So let's say you had some physical system, I don't know what it would be, you had some physical system that had the potential that she just described. Right? If this was the potential, what would the force be like? Negative 1/2 kx squared, right? What would the force be like in this case? Two ways you can, sorry? A line with positive slope. So two ways you can do this. One is you can say, well, you just told me to take the derivative with respect to x to get the force, so I'll just follow your instructions without thinking about it too carefully and say this is f equals kx, right? Line with a positive slope. Or you can say, well, I'm not sure, I'm going to use my physical intuition. Imagine this was a hill, right? And it had a ball here. But what happens if I put the ball exactly on the very, very tippy top of the hill? Nothing, right? Feels no force. Force at x equals 0 equals 0. Now, as soon as it gets moved, so somebody comes along and displaces it over here, slightly from the center, then what happens? Does it get pushed back towards equilibrium? No, it rolls off the side of the hill, right? So then with positive x, it gets a positive force, and then with negative x, it gets a negative force. There's no chance to ever get back to 0. So you can describe a completely different physical system using a different potential. Okay, so the potential is the key. And often in physics, as you'll see as you get to higher and higher levels in physics, it's much easier to work with potential directly than with forces. You can add potentials from various things. You can have a spring plus gravity, add them together linearly, right? It's not a vector quantity. And from that, you can derive the force, and therefore the equations of motion. So these are just simple examples to show you the relationship between force and potential. Is there a question?
Can you just say the directions are opposite and flip the graphs?
The directions
Like you
opposite.
define, like where you define positive x, and I say that's negative x, and just flip the graph.
Flip the graph. Sure, but I mean, this is true regardless of your definition of x, right? And if you're going to flip the graphs, you have to flip all the graphs. So it's like you're sitting on the opposite side of the board. Everything I wrote would be true still. You just see it from the other perspective. So did I answer your question? Okay. So another way to think about this potential is sort of like a particle trapped in a hole, right? So if you had your spring set up, right, and then you displaced it a little bit, and then if you draw the potential for this guy, it's a parabola, right? Now, displacing it a little bit means you come over here. These are units of potential energy, right? So essentially, you've given it this much, this much potential energy. You've given it this much potential energy at the intermediate state, and it's never going to get more energy than that, right? No matter what happens to it, it's never going to get more potential energy. So it's sort of trapped. Trapped here, right? And that determines how far it's going to oscillate. I'm just saying that when you pull it back initially, you give it a certain amount of potential energy. That sets the upper limit for how far it can ever go, which you could also see just by looking at this graph and understanding that it's going to roll around here. It's never going to go up higher than its original position, right? And so, for example, say you had a complicated potential. Do the forces under it. You had a complicated potential that looked like comes down, comes up, comes down again, comes up, and then whoop. Okay. So this is U of x versus x. Then, if you had a particle that started here, that particle would never be able to escape this web, right? Why does that mean? Well, you can use the physical model of a ball rolling down a hill. If you put a ball here and let it go, it's never going to get over this hill. Or you can use your physics knowledge and say, to be on top of this hill, for example, here, would require more potential energy than it has, so it'll never get there. All right? It's essentially trapped in this well. Whereas a particle, if you started it here, give it this much potential energy, it would be constrained to this larger well, right? It's capable of existing here, because here it has this much potential energy, so there's still room for it to have kinetic energy, right? So as you know, if you imagine what would happen if you did the experiment, the ball rolls down the hill, speeds up, it's going fast here, starts to slow down, but still has enough kinetic energy so that it's still moving at non-zero speed when it gets here, and then it rolls up here. But it can't go over this hump. Whereas if you started a particle up here, then it could roll through over both of these hills and escape. All right, so you can also think of them as like energy level diagrams. Okay, and then to be thorough about it, let's think about the direction of the forces. All right, so remember that okay, so here the derivative of this guy is negative, right? So the force I should do this. Okay, so here the derivative is negative. We want the force is the negative derivative, right? So here this is going to have a positive force, which makes sense because if it's on this hill, we push in this direction. So the force is positive here all the way to here when the force goes to 0, right? So let's put a 0 here. The force is positive in this region. And then here, the derivative is positive. We want the negative derivative. So then the force is negative, right? Until here when the force is 0 again. Right? And here the force is 0. And here the force is 0. I'm finding all the 0 derivative points to anchor my curve. Now from here to here, the derivative of the potential is negative, so the force is positive. And from here to here, the derivative of the potential is positive, so the force is negative. All right? And why do I get these curves? Well, I'm just quickly doing the derivative. Here it's 0, there it's very slightly greater than 0. Here it's probably the largest positive value. Then the slope decreases back to 0. So that's why I get some of these curves. Here's that for a second, make sure I get it right. Read yourself, it's accurate. Okay, let's do a couple of examples on the clicker just to get yourself used to thinking about the relationship between force and potential. So let's do some practice problems. So here you have a graph showing potential energy. Let's turn down the lights a bit so people can in the back can see. Potential energy. The particles, so this is a potential energy drawing, right? Not a force diagram. The particle is initially at x equals d, and then moving in the negative x direction. The question is, at which of these labeled coordinates, a, b, c, or d, does the particle have its greatest speed? So I've given you the potential energy function from which I want you to think about the kinetic energy and also the forces on the object. Okay, so who wants to tell us what they answered?
I think it's B.
Why is that?
Because low potential energy and due to conservation of energy, assuming there's no energy loss in the system,
That's right. So he says it starts at D, right? So it must have at least this much potential energy, right? And because of conservation of energy, if it ever has less potential energy than that, it must have turned into kinetic energy. We're interested in the particle's speed, so we want the place with the most potential, most kinetic energy, which is going to be the place with the largest difference in potential energy. Another way to think about it is, it starts here, it was moving in this direction, it came down this hill and there was a force on it the whole time, right? This force was because there's a slope in the potential. The slope in the potential means a force. And so it accelerated, right, until it came here when it starts to decelerate. So yes, it's at B. Okay, what about, at which of these coordinates is the particle slowing down? Which I mean, its magnitude of velocity is decreasing. Okay, so who thinks the answer is D? Nobody? How about C? Why is it C?
Because at that point the potential energy is increasing, so energy isn't energy.
It's increasing. Well, it starts at D, remember, and it's going this direction.
Oh, okay. So B, A.
Okay, good. It is in fact A. I suspect some of you made the same mistake. Okay, does anybody disagree? Yes.
Can it go back from A to D since it's gonna, the force is gonna pull it back? So isn't C also an option?
So he's thinking in the future. He says, what happens when it gets to A, turns around and comes back, right?
Yeah.
Well, do we know it's going to turn around and come back? Do we know?
Yeah, because we started at D. You only have that much.
The particle is at D. That doesn't. We don't know about its initial kinetic energy, right? I see your point, but it's possible that it could just go off the rails and go over some hump and never come back. But you're right. If it changed direction, then it would be slowing down at C. Yeah. Okay. What about? At which coordinates is the force on the particle 0? Okay, so some people think D, some people think E. Why don't you, let's try something. Why don't you discuss with your neighbor, if you got a different answer, argue about it, and then we'll vote again. Okay, so some convergence. So let's hear from somebody who didn't vote D last time, but was persuaded to vote D. Yeah, so at the points where the slope is 0, there's no force, right? Anybody disagree with that?
Shouldn't there always be a force due to gravity?
Well, we don't know if there's gravity here. We could be in outer space in some weird other potential, right? Any other questions? Don't overthink the problem, right? There could be supernatural forces. All right. So, right. So it's here is the slope is 0, and here the slope is 0. Okay. Let's do another one. Now we're looking at a force diagram. Okay, this is not a potential energy diagram, it's a force function. The graph shows a conservative force f of x as a function of x in the vicinity of x equals a. As the graph shows, f is equal to 0 at x equals a. Which statement about the potential energy function of x is correct? Is it 0 at x equals a? Is it maximum, minimum, or D, which refuses to really say anything? Okay, so B is winning, but there are some people who still believe it's C. So who thinks C is correct? Who thinks the potential energy is a minimum at x equals a? You wouldn't listen to your neighbor. You voted twice, but you wouldn't admit it. Nobody? Anybody?
Because, what do you call it, since force is the slope of the potential energy graph, it goes from negative to positive.
Okay, so imagine the force looks just like this one, right? So what does the potential energy look like? It looks like a hill, right? So one way to do it is to take the force, right? Think about what the equation is. It's going to be something like F equals kx. Integrate that, right? And flip it, right? You integrate it and you give a minus sign, you get negative 1/2 kx squared. So the potential energy is going to be a maximum a maximum at x equals a. Questions about that? Another way to think about that is this is the kind of force that's pushing you away, pushing the particle, pushing the object away from point A, right? And so it's unstable equilibrium. If it's at A, it's 0, but if it's anywhere deviated from it, gets pushed away. So that's, potential energy of this shape has that effect. Okay? What about this one? So this point here is A. This is A, this line here. Okay. Right, so it's a minimum here for exactly the same arguments. In this case, the force function would be something like negative kx. And so if you integrate that to get the potential, then you'll see that it looks just like a spring. Right, it's negative 1/2 kx squared. So force is the negative derivative of potential. You're asking why is there a minus sign here?
Oh, yeah, I forgot.
Oh. So another question might be, why is there a minus sign here?
Well, with conservational forces, the force is always acting away from the 0 equilibrium. So,
Is it?
that's something. Well, saying something about how it's.
In the case of a spring, the force is pulling you towards it. In the case of a hill, you're rolling away from it.
Yeah, I guess.
I feel like maybe there's a spring where if you take a force on it to the right, the potential energy is directed towards the left. So that like same with the vice versa. If you push the spring to the left, the potential energy is to the right. So the force is negative direction of the work.
So I feel like you've given me a couple of examples which demonstrate that this is true. That doesn't really tell me why it's true, though.
The conservative force must be reversible, or doesn't it have to be negatively related to the force?
Why?
The conservative potential or potential energy
Why does one follow from the other?
is reversible.
Why does a reversible force determine this relationship? No? Still thinking?
I was gonna say the force does work on the system, and then the system does work. Or it doesn't do work. That's what I was trying to figure out with the wording. But you're doing work on the system, and then that's just you're using that energy.
Okay, anybody else?
Interesting.
let's think about what is potential. What is potential energy, right? Potential energy really a physical quantity? I mean, I can have an infinite amount of potential energy, right? I just define myself to have it. Say, you know, the potential, it's mgh, and I define h equals 0 to be an alpha Centauri. I have a massive h. Look how strong I am, right? So is potential energy really a physical quantity? Not really, right? It's a construct that we use that's convenient mathematically. You'll see this later on in physics, for example, when you talk about particle physics, you talk about particles having a wave function. A wave function is not something that's physical, or it can never be measured. Its square can be measured, right? A wave function squared gives you the probability distribution for a particle. So not every quantity you can calculate necessarily is physical. Anyway, think about that one some more. Think about your best answers. Send them to me. We'll see what people come up with. Okay, it's a bit of a philosophical point. Okay, so let's do some example problems. So here's one that looks nasty from the book. Okay, it says a 3 kilogram block is connected to 2 springs. Like this, having force constants K1 and K2, where K1 is 25, K2 is 20. Okay, the system is initially in equilibrium on a horizontal frictionless surface. The block is now pushed 15 centimeters to the right. Okay, it's displaced 15 centimeters to the right and released from rest. What is the maximum speed of the block? First, let's just think about what is going to be the motion of this guy, right? Are the springs going to be acting together, or are they going to be fighting each other? Who thinks they're going to be fighting? Why? Well, imagine what happens. What's the direction of the force here from this spring? It's going to be pulling it back to equilibrium, right? And from K2, it's going to be pushing it back to equilibrium, right? So they're going to be acting together. How can they be acting together when it's F equals negative Kx? Right? It should be negative Kx, and you have the same x.
One of the x's would be negative if you're stretching one, you're compressing the other.
Right, you have to be very careful about your axes here, right? The Kx is relative to the equilibrium position, right? And so one of them has an x starting from here, the other one has an x going in the other direction. Okay, and let's think about the potential. Right, what does the potential energy of this thing look like? This is 0. What does the potential energy of one spring system look like? It's a parabola, right? What happens if you add another spring to it? You have another parabola, right? Slightly different slope because it's a different k, right? So it's going to be a tighter or a wider parabola. You just add the two together. That's the potential energy of this system. What happens if you add two parabolas? You get a funny shaped parabola, right? So the sum of them is going to look something like this. So already, let's just look at the potential and understand what's going to be the motion of this system. Is it going to be some weird, crazy thing like when you have a pendulum on a pendulum and it's all chaotic? No, it's going to be pretty simple. It's just going to look like one spring, right? In fact, you could probably find some way to combine these two k's into an effective k for a single overall spring. If you look at the potential shape, you can get a sense already. What are going to be the dynamics of the system? You know you're not going to have to go crazy calculating weird forces on it. You just have to think about it with these two springs acting together. Okay, so the potential, drawing a potential diagram can be helpful just in getting a sense for what's going to be the motion of this system. Okay, so let's get back to the question. How do we answer the question? What is the maximum speed of the block? The place where it has no potential energy? Okay, because... Right, so we're giving it potential energy by displacing it. Now we're asking, where is it going to have the maximum speed, which means the maximum kinetic energy? It's going to have the maximum kinetic energy when it has the least potential energy, because of conservation of energy, right?
So that'll be at the original equilibrium position.
At the equilibrium position. Just like in a simple spring question, right? Take any spring, you pull it apart, you stretch it, and then you ask, where is it going to have its maximum velocity? It's going to have maximum velocity at the point of minimum potential energy, because that's where most of the energy is turned into kinetic, right? Just like the little diagram we thought about when the ball's rolling down the potential shape. Or if you just look at this guy and say, well, it's going to be here, right? It's going to be the place of minimum potential. It's zooming down the hill, it's going to be going fastest here, and then slowed back up. Right? Okay, so let's do energy conservation. Initially we have only potential energy, so we can not even write the kinetic term. Right? There's no friction here, so it's a simple setup. Right? Now the maximum speed is going to be when we have minimum potential energy. So we'll set that to 0. Right? We'll say when UF equals 0. Okay? And that we know is going to be at x equals 0. So what is the potential energy in the initial state? Well, it's 1/2 K1 x1 initial squared plus 1/2 K2 x2 initial squared equals the kinetic energy, right? 1/2 mv final squared. Okay, now we have to think, so this is what we want, right? We're interested in this speed. We know the mass, not a problem. We know the k's, not a problem. What about the x's? We have 2 x's. Well, it's really a one-dimensional problem, right? And it's a single block. So you can think about it as just 2 frames, right? Obviously, there's going to be a very tight connection between x1 and x2, right? If this is positive x1, and this is positive x2, right? So what can we do? Well, first, are we sensitive to the signs? x1 squared, x2 squared. We don't even really care in the direction, right? So what can we say? Let's just treat them as 1, right? Because a displacement of 1 centimeter in one direction affects both springs by the same amount, right? So we can just say so in fact, we can treat it as a single effective spring, and the effective constant is just the sum of the 2. K's are newtons per meter, I believe. Yeah, I think so. Right? So let me ask you a question. Does it matter that I drew this other spring on that side? What if I had said 2 springs, identical length, different spring constants? The problem would be exactly the same, right? But it's trickier. It looks trickier when it's attached to the other wall, right? Because you're imagining some potential craziness. Okay, so from here it's pretty easy because we know how much it's been displaced. They told us 15 centimeters. We know K1, we know K2, so we can just solve. Okay, so you just plug in the numbers we get, right? And we get 6 meters per second. Now there's a second part of the problem which says, what is the maximum compression in distance of spring 1? All right, so we started out compressing spring 2, and now it's going to get kinetic energy, go through the equilibrium point, and then start to compress spring 1. The question is basically, how far is it going to squish spring 1 before it stops? Sorry? He says 15. He's trying to make an argument from symmetry. That would be valid if they had the same spring constant. But they don't, all right?
So
Wait, then wouldn't it matter where you started?
It does matter where you started. Yeah, but we started at 15 centimeters on K2. So what do we know about the point when it has the maximum compression? What's its speed at that point? Zero. Zero kinetic energy, right? So it has zero initial kinetic energy and zero final kinetic energy. So the equation of energy conservation is pretty simple, right? So you say, well, 1/2 K1 x squared is 1/2 K2 x squared, right? Not quite. You might be tempted to do it this way, but remember, in the initial configuration, both springs are extended and both springs are applying a force. Also, in the final configuration, when it's come and squished K1, both springs are extended and both are applying a force, right? So you have to account for both in both cases. So make this initial x final right? Both springs give potential energy in both cases. Right? So what do you notice here? Well, the halves cancel, right? So in fact, there is a symmetry, right? There is a symmetry, and you were right. It's 15 centimeters here, 15 centimeters the other direction, because both springs are acting on it in both cases. We're not passing it off from one spring to the other. So in fact, it is x initial equals x final. You were right, and I persuaded you you were wrong. Stick to your intuition.
So it doesn't matter what side you start on.
What's that?
It doesn't matter what side you start on.
Doesn't matter which side you start on, and it doesn't matter the ratio of the spring constants. One can be very weak and one can be very strong, or they could be equal.
Would it technically
So
be
that-
negative?
I'm sorry?
Would it technically be negative?
Yeah, you have to be careful how you define it. Yes, thank you.
Is this all under the assumption that they both have the same equilibrium?
Yes, they have the same equilibrium position, exactly. Okay, let's do another one. Okay.
No matter where you start.
A sled with a rider having a combined mass of 125 kilograms. That seems like a lot for a sled and a rider, huh? Travels over the smooth, icy hill, shown here. Yep. How far does the sled land from the foot of the hill? Right? The question is, what is this? Oh, and its initial velocity, 22.5 meters per second. How fast is 22.5 meters per second?
Pretty fast.
Yeah, is that a running speed?
Yeah, that's like several.
How fast is Usain Bolt run when he wins the
10 or
gold medal?
11.
He runs 100 meters in 10 seconds, right?
Yeah.
So that's 10 meters per second. So this is blisteringly fast for a little fatty on a sled. Somebody must have loaded up a big slingshot. Okay. Okay, so this is an energy problem, but it's also a kinematics problem, right? So let's think about how we're going to do this. We can use conservation of energy to say how much kinetic energy does he have left at the top of the hill, right? And then we need to know how far is he going to go. Well, if we have kinetic energy here, we know his horizontal velocity. And then we just need to figure out from kinematics how far he's going to travel. We can do that by figuring out how long it'll take him to fall and how far his velocity will take him in that time, right? So step 1 is find Vx. Step 2 is find the time of flight. Right? Because step 3, the distance is the velocity times the time. All right, so how do we do this? Well, how do we find the velocity? Do we have how high the mountain is? Yes, 11 meters, thanks. 11 meters high, which is a huge hill, right? Okay. So, initial potential plus initial kinetic is final potential plus final kinetic. This guy's 0, 1/2 mv squared is a number we know, right? Because we're given the initial velocity. The final potential energy is mgh. We know mass, we know g, we know h. So this is looking pretty straightforward. Right? So we know everything in this equation except for the thing we're interested in, which is the final velocity, final being up here at the top of the hill. Right? So Vf squared, so the masses cancel, bring the 2 up. Vf squared equals Vi squared minus 2gh. So I get 17.1 meters per second. So it doesn't slow down a whole lot. Right? Now, is it important that we know the shape of this guy at the top? The shape of the hill. Well, what did we just calculate? We just calculated basically the magnitude of the velocity, right? To know how far he's going to land, it's also important to know the direction. If, for example, the hill would look like this, he would have a different trajectory than if the hill looked like this, right? So in this case, the top of the hill is flat, which means we can assume that he has 0 y velocity when he's up here and he starts to fall. And all of this goes into his x velocity. Right? So if he has 0 y velocity, all we need to do to find the time of flight is to calculate how long it takes to fall from rest 11 meters. Right? Which is not hard. Right? It's just 1/2 at squared, right? Where we know y, it's 11 meters, we know a half, we know g, so we can just solve for t, right? And I get 1.5 seconds, so he's gonna have the thrill of his life for 1.5 seconds, and then for the third part, the distance he travels, here this is easy because once he leaves the top of the hill, he's no longer losing velocity, right? His velocity in the x direction is constant, right? So this is 1.5 seconds times, thank you, 17.1 meters per second, so I get 25.6 meters. So why doesn't his velocity, so here his velocity, his x velocity is basically constant, right? But from here to here he's gaining y velocity, right? What's going to be the magnitude of his y velocity just before he hits?
22.5.
What's that?
22.5.
And why is that?
Because conservation is energy.
Yeah, exactly. Good, okay. His magnitude, his total velocity here, right? His x velocity, just before he hits his x velocity, is still going to be 17.1. Nothing's going to change that until he splats, but his y velocity is going to increase until it makes up for the potential energy that he's gained here, turning into kinetic energy.